Hi guys. So behind me I've got, this is actually a reversed image, but behind me I've got a frontal view of an aircraft, and the reason I'm showing this is because I'm showing there's a total pressure probe, and here there's an angle of attack vane. So this is measuring angle of attack and total pressure, and somewhere else there'll be a side slip vane, probably on the bottom. So these are part of the aircraft air data system, and these are capable of taking the oncoming velocity and then measuring, like I say, total airspeed, angle of attack, and somewhere else side slip. So knowing what we know about Coriolis theorem and relative motion, we're going to look at how we can take those measurements and convert them into aircraft body velocities. So let's draw this out. Actually, let's draw my fuselage first. So we're going to, for simplicity, say that all of these items are co-located. But I'm going to draw an aircraft with a cockpit, a door for no reason, and what we're interested in is where the aircraft axes are. Okay, so we've got aircraft X, Z, and Y, and we're interested in knowing where the air data system is. So let's say that we've got the air data system located somewhere in the nose of this aircraft. Okay, so let's say that what this is measuring is it's reporting angle of attack, and let's say it's reporting the angle of attack is 30 degrees, side slip is 30 degrees, and let's say that, I'm taking these numbers out of a question here, let's say that the total velocity that it's reporting is 50 meters per second. Okay, so we've got these measurements here, and we're also going to say there's a gyroscope in the aircraft somewhere measuring the aircraft pitch rate. So we'll say we know that Q is equal to 30 degrees per second. And let's say that our air data system is located along the x-axis, so we know that it's got no y and no z displacement, and the distance away from x equals 0, or the y-axis, is 5 meters. So how can we take these measurements and convert them to aircraft body velocities? So we want to convert them to UV and W, knowing that, well, we have a pitch rate. So Coriolis theorem is going to tell us that because our air data system is ahead of or it's not located at the aircraft center of gravity, there will be terms due to, P, Q, and W. We've only got Q in this example. We're assuming that P and R, sorry, not W. We're going to assume that P and R are 0. But we're going to derive some relationships that are going to help us turn these into these here. So the first thing we're going to note is that these measurements that are being taken are actually not the angle of attack and side slip of the aircraft. These are the angle of attack as measured by the probe. So we're going to give them subscript P, and the same for the total velocity. So these are components that are being measured on the nose, but they're not the same as the aircraft total components. So we're going to use it's just basic relative motion to say that our probe position vector in the absolute reference frame is equal to the aircraft position vector plus whatever the relative position vector of the two are. And what we're interested in is we are particularly interested in the velocities. So we need the first time derivative of these. So So these components that we're actually measuring, so these are the parts that combine to give us the total velocity and the aircraft angle of attack and side slip, are the vector addition of the aircraft absolute velocity, which we know is just uv and w, and then this term here, which is we need to use Coriolis theorem to develop. So this one is so we know that one, and this one here we need to use Coriolis theorem. So we'll say that the absolute time rate of change of RPA is equal to, recalling our Coriolis identity, d of P on A with respect to time. Okay, and then this is in body axes. So in fact, rather than OXYZ, let's write body here. Plus a rotation vector crossed with P on A. So let's think about what this term is saying. So just narrating this fully. Over here, the velocity as measured at the probe is going to be equal to the aircraft velocity plus this expression here. So this is the absolute rate of change of the probe's position with respect to the aircraft center of gravity. And that is going to be equal to the time rate of change of the aircraft, of the probe position in body axes, plus any cross-coupling terms due to Coriolis theorem. So here, this is the time rate of change of P on A. And let's just call this for the moment R dot P on A. Okay? And let's say this is, let's go back a second. Let's just say that our probe position, P on A, is XP, YP, and ZP. Okay, this is the position of the probe within body axes. Now up here, I'm keeping it as X, Y, and Z. When we do this question, we're actually going to just say that X is 5, the other two is 0, but I'm going to develop a general relationship that will help us answer this question first. So these terms down here are going to be X dot P, Y dot P, and Z dot P. And these terms here are cross-coupling due to the aircraft body rates. So we've got P, Q, and R. Let's do the cross product. So we end up with Q ZP minus R YP, R XP minus P ZP, and then P YP minus Q XP. So we can now put all these together. We can put this together with this to give us RP on A. The time rate of change of RP on A, rather. Okay, so we can now remember that this side over here is what we're going to be measuring, or sort of things that related to what we're going to be measuring. And then we can now build this completely up. So let's just expand upon this a little bit. So R dot P is the absolute velocity as measured at the probe. Okay, or at the air data system. So let's say this is UP, VP, and WP. So we can put this all together. Basically, this is equal to this plus this. So let's put this all together. So we've just determined that the velocity as we measure it at the probe is going to be equal, let's just write this out. So this is abs velocity at probe is equal to the absolute aircraft velocity plus any time rate of change of the probe position and then here we've got Coriolis terms. And this comes from the cross product of omega crossed with RP on A. Okay, so this time rate of change, if we're in flight mechanics, we can assume that all of this is 0 because we have a rigid aircraft. And let's think about what we're actually trying to do. We want to get this as a function of this. So we need to rearrange for this. Now my pencil is running out of battery, so I'm going to pause here and then I'll come back. Okay, so with all of these cables floating around and doing other things, sometimes my iPad comes unhooked and then I've got to remember to plug it back in. So let's just talk about the terms we've got here before we go ahead with the question. So we've got the parts that the absolute velocity at the probe. So this is UP, VP, and WP. We've said this is a combination. It's the sum of all these different things. So we've got the aircraft absolute velocity, UV and W. We've then got any terms that occur due to the time rate of change of the probe position. So if we had a flexible aircraft, i.e. we had quite a longitudinal bending mode in the aircraft, then we have non-zero terms here. We're probably much more likely to have a ZP term and a YP term than an XP. For example, we probably won't see the fuselage contracting and expanding longitudinally. We're more likely to see these other two. But in our course anyway, we're going to assume they're all 0, so all of these are going to sort of disappear for our course. So we can get rid of these anyway. These terms here are then the Coriolis coupling between body roll pitch and yaw rates, P, Q, and R, and the probe position. So what we actually want is these bits here, U, V, and W. And we've got to remember that actually we aren't really directly measuring these. What we're measuring is alpha P, beta P, and the total velocity. So we need some relationships that are going to help us. Just before we get there, we're going to do this first step, which is rearranging the equation that we've just got for u, v, and w. So let me make myself smaller again. I don't need to take over the whole screen. So what we're going to show is that u, v, and w, which is the bits that we want, so this is the absolute velocity in aircraft body axes, is equal to the UP, VP, and WP minus Q, ZP plus RYP minus R, XP plus P, ZP minus P, YP plus Q, XP. Okay, so this is assuming a rigid aircraft, so we'll say this assumes, so this is because of our rigid aircraft. I need you guys to let me know whether you prefer me behind the notes doing it. I feel like I can just be a little bit bigger with this and I can move my hands all around the screen. I'm not enough of a narcissist to think that you need to see my face, but I think it helps with me communicating when you can see me moving around and stuff. So let me know through feedback what you actually want there. So let's just go back to our question and remember what we're trying to get is we want these because of these. So what we've actually just produced is a function that gives us these if we had UP, VP, and WP, but we haven't got those. We've actually got these terms instead. So the relationship between the angle of attack, side slip, and the total velocity at the probe is exactly the same using the aerodynamic relationships that we had before. So we can produce a relationship or produce relationships between the velocity vector as measured at the probe, which is UP, VP, and WP, and the measurements. And remember the measurements we've got are alpha P, beta P, and VFP. So let's just say this is AoA of the probe, side slip of the probe, and this is total airspeed. So we can use the exact same relationships that we would do using the aerodynamic angles. So just from the definition of alpha, so alpha P is the arc tangent of WP on UP. And then the side slip, just again from definition, beta P is equal to, so there should be an arc tangent there, not the tangent. Beta P is the arc sine of VP on VFP there. And we've got the other relationship that's going to help us is that VFP is just the vector sum of UP, VP, and WP. So we want expressions for UP, VP, and WP in terms of the things we've got. So we need to think about how we can manipulate these equations to help us out. So this first one's going to be a little bit easier. So let me just remind myself where we're going with this. Okay, so let's say here that we've got UP, we could rewrite as WP. No, sorry, let's not rewrite that. Let's say that WP could be rewritten as UP tan alpha P. And we can say here similarly that VP could be written as VFP sine beta P. We're then going to use these in this expression, so we'll substitute these into here. Okay, so I've now got an expression that's only got total flight speed, UP, and sine and beta. So I can rearrange this to give me UP. Let's just spend a little bit longer rearranging it. Let's say I've got VFP squared, so I've got 1 minus sine squared. That's the sine squared of the side lip at the probe is equal to UP squared 1 plus tan squared alpha P. So UP is equal to VFP Okay, this one's the hardest one to remember how to get. So this is the probe forward speed as a function of the total probe speed and the side lip and the angle of attack as measured there. We can then just use the other two relationships that we've got to get VP. Well, VP we have already, so we have VP is equal to VFP sine beta P, and then WP is just going to be equal to the expression that we had previously multiplied by tan, I think. Yeah, so we've got this expression up here. So we've got VFP tan alpha P 1 minus sine squared beta P divided by 1 plus tangent squared alpha P. Okay, so these here are our expressions for the velocity at the probe as a function of the total velocity and the things we measure. So these terms can, let's call this asterisk 4. Asterisk 4 can now go into these bits here. Okay, which is going to, so we're going to take asterisk 4 and substitute them in. Rather than do it this way around, let's copy this down. I'm going to rewrite this. I want to just be able to see it at the same time as everything I've got here. Okay, so we want to take these and put them in here. So we will say that now we've got finally what we wanted. Now we may express the velocity, so the absolute velocity, on body axes due to the body rotation vector, the total flight speed as measured at the probe, alpha p and beta p, which is the side slip and the angle of attack of the probe. So let's do it. Let's write it down. So the first things we're going to put is that these terms up here, asterisk 4. Okay, so that's these terms dealt with. Now we just need to copy these bits down. So minus Q ZP plus R YP minus R XP plus P ZP minus P YP plus Q XP. So this is the equation that's going to help us answer this question. So let's remember what we were actually saying at the beginning was if we had alpha and beta were 30, VFP was 50 and Q was 30, how can we answer this question? So let's go down here, rewrite those all the way down here. So recall alpha P, beta P is equal to 30 degrees, RP on A was 5, 0 and 0, VFP was 50 meters per second, and I'm going to look back at my question sheet at the pitch rate Q is 30 degrees per second. We weren't told anything else about the other rates, so we'll just say that's P is equal to R is equal to 0. So we can now solve for everything here. Okay, so let's just look through. So here we've got XP, YP and ZP, which means that anything with ZP or YP we can just get rid of. So ZP goes, YP goes, ZP and YP, they go there. We're just going to convert Q, that's in degrees per second, so Q is equal to 30 divided by 180 multiplied by pi in radians per second, because we're using this in an equation that doesn't involve a tangent or any trig terms, so it needs to be in radians per second. And then everything else we can do exactly as is. We can leave these in degrees, just remembering to make sure that our calculator is set to degrees mode. So U is equal to 50 multiplied by the square root of 1 minus sine squared 30 divided by 1 plus tan squared 30 is equal to, let's just check this, 50 square root 1 minus sine 30 squared divided by 1 plus tan 30 squared. Okay, so I was going through, I got the answer out of 37.5 here on my calculator, and I thought that doesn't sound right because that's not right compared to the answer I had. gone through and double checked. I was looking at the wrong solution when I was going through. So I've got this question and the numerical answers written down, and the numerical answers I've got it wrong because I know this is correct now. So I've put my numbers in here and I get a u velocity of 37.5 meters per second. V is just going to be equal to 50 VFP multiplied by sine 30 minus RXP. Now R is 0, so it's just going to be 0 in this case. So 0 multiplied by 5. So we get 50 multiplied by sine 30, 25 meters per second. And W is equal to 50 multiplied by tan 30 multiplied by 1 minus sine squared 30 divided by 1 plus tan squared 30 minus Q, which is the pitch rate. So I've got a pitch rate of 30 divided by 180 multiplied by pi multiplied by XP, which is 5 in this case. So that equals okay, I get 26.250 meters per second. So we've got our 3 components of velocity now. We can use these to recover the aircraft angle of attack as well, which the aircraft angle of attack and side slip, which actually I didn't ask, but we can do this. We can say the total flight speed is the vector sum of all of these. So it's 37.5 squared plus 25 squared plus 26.250 squared. So we get a flight speed of 52.16 meters per second. We could then recover the aircraft angle of attack as well during this instantaneous pitching maneuver. Alpha is equal to the arc tangent of W on U. So beta is equal to the inverse sine of V on VF. So that's going to be arc sine of 25 divided by 52.16. So we get 28.6 degrees. Now let's think if these expressions make sense. So let's just see what we have. We have a slightly higher actual flight speed of the aircraft. So the velocity at the probe was 50 meters per second. We've got a slightly higher velocity. We've got a higher angle of attack. So we've actually got 35 degrees of angle of attack, and the probe was measuring 30. So we know we had a positive pitch rate of 30 degrees per second. So let's just think about what's happening. If the aircraft is pitching up, that's going to experience a downwash, which is a reduction in angle of attack. So that makes sense to us. If the aircraft is pitching up, that's also got an increased velocity here. So Because we had a positive angle of attack, we've actually got an increased total velocity as measured here as well. Let me just double check that one actually. Yeah, so we've got a slight reduction in side slip as well because we've got this increase in the total. We've got this increase in the total airspeed by contrast to what the probe is measuring, which means that the effective sidewash is actually lower by comparison to the total flight speed of the aircraft. So we've gone through the derivation of some equations that are going to help us recover the aircraft velocity when we're given probe measurements if we know where that probe exists on the aircraft. So let me just pause this. I'm going to go through another example question. Okay, so in that last question, we took the quantities measured at the probe in terms of angle of attack, side slip, and total velocity, and then related them back to aircraft body velocities, U, V, and W. We're going to look at what happens the other way around now. So we're going to go through an example. Imagine if we've got an aircraft and for some reason parts of the air data system are damaged. Okay, the sort of situation which this can happen is, say, during a bird strike. So just going back to the air data system here, imagine if we had a situation such that the angle of attack sensor was working, but the total pressure, or the airspeed indicator was not, and the side slip was not as well. So we'd have to use inertial measurements taken on the aircraft, so accelerometers somewhere else. We'd have to work out the total aircraft velocity and the side slip from these. So let's see how we can determine them. So we'll say we have an aircraft where we can measure the angle of attack, and that's 5 degrees, but the side slip is unknown because it's damaged, and the total velocity is also damaged as well. So it's important to note that in this has already been through, so this is alpha and not the probe alpha. So this has already been converted and corrected for aircraft pitching, motion, etc. To give us the probe. We've got measurements from the gyroscope, so say gyro measurements. So these give us that the aircraft body angular rates are, for this example, -1, 2, and 3.5 degrees per second. And then we need some more information. So there's not enough information to recover the aircraft's size and body velocity yet. We need to rely on inertial measurements. So these will be taken in from an accelerometer pack somewhere on the aircraft. So we could have the absolute acceleration of the let's not call it absolute acceleration. It is absolute acceleration, but I don't want to confuse it with being measured at the aircraft center of gravity. So let's say we've got AX, AY, and AZ. These are 0, 5, and -3 meters per second squared. And these have been measured at an inertial measurement system, or an inertial measurement unit, I should say. And the IMU lives at a location which we'll say is RI, and this is at 5, 0, and 1 meters in our aircraft. Just write this down for you guys because it's an acronym you probably want to remember. This is the inertial measurement unit. This is a collection of gyroscopes and accelerometers that we can measure different quantities on the aircraft. So it's measuring two things here. We've got the aircraft angular rates, P, Q, and R, and the aircraft velocities, but they're not at the center of gravity, so they contain implicitly the Coriolis components due to the fact that they're not located at the aircraft center of gravity. So let's see how we can get these components and how we can compare them. So remember, we want to get these two. We have this, and we have this. So want, have. So we need a relationship to go between the accelerations now. So before we were just looking at velocities, now we're going to look at accelerations. We want to look at the absolute acceleration of a probe at this location. So we'll say I is equal to R A plus R I slash A. And I'm being a bit naughty up here. I should have said this was in body axes. Okay, because this is therefore with reference to the aircraft up there. Okay, so let's just say the different parts that we have here. This is the abs position vector of IMU. This is the aircraft absolute position vector, and this is the relative IMU position, and that is this bad boy here. So follows from this, again we're looking at accelerations this time, that R I, let's look at R double dot A plus R double dots I slash A. So this is saying the absolute acceleration in the inertial reference frame, so it's absolute by definition, of the IMU is equal to the absolute acceleration of the aircraft plus the absolute relative acceleration of the inertial measurement system. So we're going to have to use the second order Coriolis identity for this. So let's just remind ourselves of the second order Coriolis identity. Let's draw this one in another color. Let's say D2 of the vector in time in the absolute reference frame is equal to the second time derivative in the local reference frame plus the absolute time rate of change of the rotation vector crossed with the position vector plus 2 of the rotation vector crossed with the first time derivative plus the cross product of the rotation vector with the cross product of the rotation vector and the position vector. So we're going to need to use this dirty great second order Coriolis identity to help us. Because we've got two time derivatives here, we could use the Coriolis identity twice, or we could recognize that the second time derivative of position of the aircraft is equal to the first time derivative of velocity of the aircraft. So we can use the first order Coriolis identity to get this for us. Or we should actually, we've got this in previous questions before, so I'm just going to write this down actually. We're going to say that the acceleration of the aircraft, so we'll say okay, so we've got this term, we now need to get this term here. So let's populate this. Remember that R double dot I on A is equal to, let's write it in general form. So we'll call it xi, yi, and zi. Now we can be a little bit smart here, and we can see that if we're using the Coriolis identity, then we've got a rigid aircraft. So these two terms go to 0. And in all of this course, we'll be able to assume that the angular acceleration is 0. Okay, so we've actually only got this last term to deal with. So let's determine this. So we'll do the omega cross I on A first. I, J, K, P, Q, and R, Xi, Yi, Zi. So we get Q, Zi minus R, Yi, Rxi minus P, Zi, Q, Zi minus Rxi. Okay, so that's this bit done. We now need to do omega crossed with this. So we need to do omega crossed with omega crossed with R I on A is equal to I, J, and K, P, Q, and R. And let's bring these terms down. Put some brackets around these to make it a little bit easier. So we can do this second cross product. We're going to end up with Q let me just go back a second. There's a mistake in my first cross product here. I'm going to keep these mistakes in because it keeps me honest. Let me just double, I can see there's a mistake in this somewhere, so let me just have a look. So my first row is QZ minus RY, that's correct. Second is P, yeah, RX minus PZ, that's correct. It must be in this last one. So this is completely incorrect. So let's just do this whole second row again. Again, it keeps me honest if I keep these mistakes in. We get P, YI minus QXI. So that means this last term over here is incorrect. Okay, so now I can do my, let's put this round. Just because I've done this question enough times before, I know the terms that I should be getting down here, and it didn't make sense to be getting a Z term here. So I'm going to do the first row. So I'm going to get Q PYI minus Q XI minus R RXI minus P ZI. I'll show you how I knew I made a mistake in a moment. You might see what I've realized already. Okay, this next one we get R yi. Sorry, no we don't. We get r qzi minus r yi minus p pyi minus qxi. And then this last row, we get p rxi minus pzi minus qzi minus ryi. So this is the, well, effectively this is the entire term for r double dots. P on A. The reason I noticed I made a mistake was because we expect all these terms. We're going to simplify this because we can see here we've got q squared multiplied by x, r squared multiplied by x. We've got r squared y, p squared z, q squared z. So we have this, the z is where we get the squared terms, we have y where we get squared terms, and x where we get squared terms. And when I put these lines down there, I could see that I wasn't going to get that. So I must have messed up somewhere in my first cross product, and that's how I know I made a mistake. So we've now got all of the terms we need to determine the absolute acceleration. So let's go back over here. We can now populate this because we've got these terms and these terms. So we can put them all together. Actually, let's make the arrow go down there. Okay, so we can put this all together and get the absolute acceleration of the inertial measurement unit. The absolute acceleration of inertial measurement unit is, what did I call it earlier? Have I written down what I called it? Let's say it's AIX, AIY, and AIZ. Is equal to, also there's a small mistake here, these should have dots on them. Okay, this is standard, we've derived it before. I could have got it from the first order Coriolis identity, but there weren't dots on those, which didn't make any sense here. Just collecting the squared terms here, so I've got a q squared x and I've got r squared x here, and they're both negative. And then I've got these cross-coupling terms, so I've got plus yi qp plus zi pr, and again we'll see this pattern. We'll see that the direct terms are the sum of two squares of the off-axis angular rates, and then always negative. And then here I should expect to see the other two as being positive terms, which are products of angular rates. So in the second row, I'm always looking out for patterns when I'm doing this sort of equation, these sorts of questions, because it tells me when I'm going right or wrong. So in this next one, we'll do the x terms first. So I've got, because I've got a negative and a negative, I've got qpxi. And then I'm going to expect a negative y multiplied by two squared terms. So I've got minus r squared and minus p squared. So that gives me minus yi p squared plus r squared. And I'm expecting a z which should be positive. Yep, that's right. So I've got plus zi rq. And then this last one, I should have a positive x term. So I've got plus xi pr plus, and I've got qr yi, and I'm expecting a negative pair of zi squares. So I've got PR and, sorry, no, I haven't. I've got PP and Q here. So I've got minus ZI P squared plus Q squared. So with a lot of these, and with any of these aircraft equations, just look for sort of patterns as you're going through and deriving them, and this will tell you whether you sort of got the right thing or not. So let's try and remind ourselves what we're trying to get here. We want to determine the side slip and the total velocity, and we've got the angle of attack and we've got these here. So we want a means to determine some things from our aircraft, and we're going to think about how we can determine it now. So we've got the left hand side 0, 5 and minus 3. So this is from IMU. We also know PQ and R. We've got PQ and R are minus 1, 2 and 3.5. Remembering that these are in degrees per second, which is not SI units. And the last thing is we have alpha, which is equal to 5 for us. So we've got alpha is equal to 5 in our case. So one thing that I have not told you in this question, because I'm sort of going through a question and showing you how to do it, we're going to assume steady flights. Assume it's a steady maneuver. And in brackets, I'll always tell you. Just for context, I'm answering one of my own exam questions here from previous years. So this was, the actual question was written during a rapid pitching maneuver, an air data system mounted in the nose of the aircraft senses an angle of attack, blah, blah, blah. You may assume it's steady in this case. So we've got that all here. Okay, so let's go through and get the rest of the question. So we're going to work with the x equation first. So looking at this equation, things we're going to need in here. Well, we've got the left-hand side already. We need u dot. Well, we know it's 0 because it's steady. Q we've got. W we don't, but we can use the W is equal to u tan 5 in this case, which gives us just u to solve for. And then we're going to go through. We know R, we don't know V, so we leave that as an unknown. And then everything else in here we actually know. Bring this down, and we say that 0 is equal to 0 plus Q, which is 2, multiplied by U tan 5, minus R, which is, let's go back a second, sorry, these are in degrees per second, so I need to do pi on 180 multiplied by u tan 5 minus r, which is 3.5 multiplied by pi on 180 multiplied by v minus xi. Now let's remember what our location was. We had 5, 0 and 1 was our location vector. tells me that xi is 5 multiplied by 2 multiplied by pi on 180 squared plus 3.5 multiplied by pi on 180 squared. So let's just go through the equation and see the things we've got. We've got here, 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 we're done. Plus yi, well that's 0, so we don't have this term here. And then zi we've got now, so let's put this in. So that's zi is p multiplied by r. So plus 1 multiplied by minus 1 multiplied by 3.5 multiplied by pi squared on 180 squared, because that gets rid of all those other terms in the expression for us. Sorry, it will deal with the fact that we've got two rotation rates in degrees per second. We're converting them both to radians per second using the square there. So let's go through and collect these terms. We'll just do the multiplication first. So we've got 2 multiplied by pi divided by 180 times tan of 5 degrees. Okay, so this gives me 3.0539 times 10 to the minus 3 u. 3.5 times pi divided by 180 gives me 61.0865 times 10 to the minus 3 v minus, let's do this dirty great expression here, 5 multiplied by 2 times pi on 180 all squared plus 3.5 times pi divided by 180 squared gives me 0. Let's do this 1, 2, 3. I don't know why I put this exponent to 2 before there, but never mind. Let's say 1, 2, so let's say that's 2.4750 times 10 to the minus 2. And then I've just got some numbers here. So that's 1 multiplied by minus 1 multiplied by 3.5 multiplied by pi squared divided by 180 squared. So that's minus 1.066 times 10 to the minus 3. Okay, so I've now just got a relationship between u and v now. So this ends up with 2.475 times 10 to the minus 2 plus 1.066 times 10 to the minus 3. It's going to be 2.5816 times 10 to the minus 2 is equal to 3.0539 times 10 to the minus 3 u minus 0.0865 times 10 to the minus 3 v. So we've got a relationship now, which I'm going to call asterisk 1, between u and v. Okay, let's do the second equation of motion. Let's take this one down. Let's just copy this whole thing so we can see it in big. We can start populating with this with some of the terms that we had. So we need our acceleration at the probe, which was measured as 5. Let's do this in blue. So we've got 5 is equal to v dot, which we said is 0 because it's a steady maneuver, plus r multiplied by u. So r is the angular rate in yaw is 3.5. So 3.5 multiplied by pi on 180 multiplied by u minus p. So that's the roll rate. So that's minus. So it then becomes a positive because it's a minus 1. So it's 1 multiplied by pi on 180 multiplied by w. Now w we already said was u tan 5. So that becomes u tan 5 plus this next one, xi qp. So xi was 5 plus 5 multiplied by qp. So that was 2 and minus 1 multiplied by pi squared on 180 squared. Plus yi is 0. That's the probe is nowhere dislocated in the y-axis. And we've then got plus zi, which was I think 1. Yeah, 1 multiplied by rq. So that's 3.5 and 2. 3.5 multiplied by 2 multiplied by pi squared on 180 because we've got two angular rates in degrees per second to convert it to radians per second. So let's do the numeracy. 5 is equal to 3.5 times pi divided by 180. So we get 6.1086 times 10 to the minus 2 u plus pi divided by 180 multiplied by tan of 5. Nope, let's do it again. Pi divided by 180. That gives me 1.5270 times 10 to the minus 3 u. And then these last things are just numbers, so I'll just collect these all in one. 5 times 2 times minus 1 times, just add all these terms up actually, 5 times 2 times minus 1 plus 1 times 3.5 times 2 multiplied by pi squared divided by 180 squared gives me minus 9.1385 times 10 to the minus 4. So this is just an expression for u now, so I should be able to solve for u. So I'm going to get 5, oh no, let's do that, 5 plus that previous answer, so 5 plus no, I should have done 5 minus that answer, but okay, so 5 plus 9.1385 times 10 to the minus 4 is 5 and not much change. It's going to equal 6.1086 times 10 to the minus 2 plus 1.5270 times 10 to the minus 5. .99. Right, you got 80 here effectively. I'm so very close to it, but I'm going to keep a few more decimal places in here. 79.993. So I was working to 4 decimal places. Slightly messed up my precision here because I was actually working to 5 degrees of precision, but let's just keep this for the moment. So that gives me u. We can get this then using this one here. We can say that v is equal to 2 points. It's going to equal v is equal to 3.0539 times 10 to the minus 3 u minus 2.5816 times 10 to the minus 2 divided by 61.0865 times 10 to the minus 3. So okay, we get the V is equal to 3.5768 meters per second, and then we can get W from W is equal to U tan 5, which we had earlier. So W is equal to U tan 5. So W is equal to 79.9993 multiplied by tan of 5. 6.999 meters per second. Okay, so immediately now we can get our side slip and total velocity. So Vf is equal to the square root of u squared plus v squared plus w squared. So it's going to equal 79.999 3 squared plus 3.5768 squared plus 6.999 squared. 80.38 meters per second. So I'm going to present my final answer to far less precision than I was working to, which is what you guys should always do, but I tend to find students don't. And then we'll say that beta is equal to the arc sine of V on Vf. So that is 3.5768 divided by what we just worked out, 2.55 degrees. Bingo. Okay, so we've just gone the other way now. That's a complicated expression. That would be a full question in an examination. I don't know if I'm going to be giving you guys a full exam on this. But that would be starting out with inertial measurements and then developing a relationship and recovering some information about the aircraft. So we've started out with measurements taken in the inertial measurement system. So we've got the full aircraft acceleration and the full aircraft angular rates. So the acceleration, we're told where it's been measured, we're given that position vector. And then you are told the aircraft angle of attack. So it's already been put into absolute aircraft axes. And we've gone from here, we've used the second order Coriolis theorem. We've actually only used one of the terms here. And then the first order Coriolis theorem. So the big step was producing this expression. Gone through, only used two of them. Okay, we're a bit smart. We said, well, we know the relationship that we're after is, we know the angle of attack, so it helps us determine u as a function of w, so we can work out u and v, and then we've got w immediately, and then we end up with these two things here. Okay, so we've gone through a lot today. I'm going to go through a couple more examples in the next couple of days and upload those as well, and you guys should be sorted for module 3, I hope. And then now we've got these equations, we're going to use them. We're going to linearize them and do some fun things with them. Okay.